This video is a demonstration of heap data management scheme on applications for limited local memory multi-core architectures. One such kind of architecture is the IBM cell processor. We will test it on an example which is called red blood tree. Number of nodes means how many nodes will be created in the red blood tree. As we can see, the new node will be dynamically allocated and assigned with a random number first, and then the node is inserted into the red blood tree. After the insertion finishes, the application prints out the red blood tree. Two versions of the application will be shown in the video. They are running with the same application, except that red blood tree low is the version running without any heap data management, and the red blood tree yes is the version running with our heap data management technique. Let's first look at the version without heap data management. Before we run, let's first compile it. Now we can try to input a small number of nodes. Let's see 6,000. As we can see, the program is successfully executed. Now let's try a larger one. Let's see 6,800. The program works well too. How about 6,801? Uh-oh, the program stops there, which means the application runs out of the local memory. To be more concrete, we can take a look at our explanation. As we can see, each time when the program calls the library function malloc, the heap size will increase. Eventually, the heap data will go to the heap segment and grab the program. This slide shows what we will do for heap data. Our heap data management only keeps the active portion of application heap in the local memory. When the heap region in the local memory is full, our scheme will evict all heap objects to the global memory. On the other hand, the heap objects need to be got back to the local memory before it is accessed. The number of objects being transferred each time can be customized by client the program in order to get a better performance. Our scheme is a pure software technique. The graph shows the flow of using our infrastructure to manage heap data. Given our C source code for SPE, our optimized compiler will automatically insert function calls at the right place and generate the executable files. This completely eliminates the insertion work for programmers. Our library includes 4 functions. The malloc and free in the black color handle dynamic memory allocation. P2S and S2P are for heap pointers. Their functionalities will be explained in the next slide with the example. As we can see, we need to replace the original malloc with our malloc function call. This function allocates space in both local memory and global memory. Finally, it returns the global address. The reason we return global addresses for heap objects is that they can only be identified by global addresses. Because heap objects are swapped in and out during the execution, different heap objects can have a same local address, with which it's hard to know which heap object it is. Since the heap pointers are global addresses, they need to be translated to local addresses before its usage. This work is done with our P2S function. Besides, it can assure the heap object is in the local memory. Since the heap object might be accessed in the future, it would be better to translate the local addresses back to the global addresses. This is the functionality of our S2P functions. Now, let's see what will happen when the application runs with our heap data management. Before we run, let's compile it. As we can see, the only difference from the previous make script is the flag LLM manage. This flag will trigger our implemented path in the GCC to insert library function calls. Now, let's try to run it with an input n equaling to 6,800. As we can see, the program works well. How about the input 6801? Well, it still works. Or even larger value of 15,000 still okay for the program. That's to see. Our technique enables unlimited heap use in the local memory of limited local memory multi-core architectures. It takes a little bit of time, since there are lots of data transfers between the global memory and the local memory.